Good afternoon, and welcome to today's electronic design webcast. Our topic today is how to know when it's time to lower your IQ. I'm Murray Slovic on behalf of Penton's Design Engineering and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the electronic design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now, let's meet today's speakers. Robert Nicoletti has over 15 years' experience in the semiconductor industry with Maxim Integrated as an applications engineer and has managed an applications team. His experience spans a wide range of system-level disciplines such as system power, interface, and audio solutions. He holds a bachelor's degree in electrical engineering from San Jose State University. Joining Robert, we have Joe Van. Joe is an executive director of design in the core products group at Maxim Integrated and is currently focusing on standard power products. Previous roles at Maxim include design leadership in nanoPower and PMIC IP development for the mobile power group, and development of chargers, switching regulators, linear regulators, all for the portable power group. Prior work includes design roles at Microlinear, Hewlett-Packard, and National Semiconductor. Joe holds a BSEE from The Ohio State University and an MBA from Santa Clara University. Now, let me turn things over to our presenter. Robert, the floor is yours.
Thank you, Murray. Hello, everybody. My name is Robert Nicoletti, and I will be presenting today's webinar on how to know when it's time to lower your IQ. I will be discussing the importance of reducing quiescent current consumption in small coin cell-powered IoT wearable devices while introducing our latest nanoPower boost converter MAX 17222 that addresses these applications. So boost converters are widely utilized in consumer electronics to raise and stabilize sagging voltage of lithium-ion batteries under load. A big driver for the consumer market is the Internet of Things, a cloud-based network of often wirelessly interconnected devices encompassing things like audio, video, smart home, and wearables. So this presentation today will focus on the MAX 17222 nanoPower boost converter, its features, and why it is designed specifically for these applications. So today's agenda, I will define what nanoPower is, since it's kind of a new and emerging term. I'll talk about some of these emerging applications. I'll talk about unique requirements of these applications, such as size, batteries, types that are used, battery life, shelf life of these applications. We'll discuss some sneaky power losses. We'll talk about multiple source applications. And of course, we'll talk a little about efficiency and how our part deals with low load applications. So nanoPower is a reference. It's kind of new. It describes new ultra-low power ICs that are emerging on the market that have quiescent current less than 1 microamp. So devices such as op amps, current sense amps, supervisor ICs, and power switching regulators are already on the market today. These low power ICs meet the strict demands required for these tiny coin cell devices, as battery life is expected to last longer, while the overall size of these devices that they're used in are reduced. So battery life has become a focal point as consumer devices continue to shrink. There are various techniques to extend battery life, and one factor that should not be overlooked is low quiescent current. Here we examine the role of low quiescent current and other integrated features designed into the MAX 17222 nanoPower boost converter that will increase battery life, essential for today's wearable, mobile, and smart connected devices. So designers for small consumer and IoT devices face a lot of tough challenges, such as power consumption, the use of multiple power sources, device ergonomics, accuracy, RF integration, cost, and more. Some applications are so size critical that the battery becomes the determining factor for product size, as seen here. There are therefore very small, low capacitive batteries are used. Every bit of savings greatly increases the longevity of the battery. So nanoPower switching regulators are coming out that address the design problems associated with these needs of today, low power electronic devices. These new regulators operate with quiescent currents down in the hundreds of nanoamps. They are designed to minimize even small losses due to ultra-low leakage losses. They achieve high efficiency even at very light current loads and completely disconnect the power source from for idle states that can last up to years. So why nanoPower regulators? Let's put some numbers into perspective. Smaller devices are using smaller batteries, and smaller battery means less stored energy. So how much power savings can you really get from one of these nanoPower regulators? So here I have an example of a 12. This is a coin cell lithium 3-volt battery. Now all batteries have a self-discharge rate, and this one, specified by the manufacturer, is 1% a year, which equals to about 39 nanoamps discharge current. So nanoPower regulators are ideal for applications where the circuitry stays idle for extended periods of time, then powers up for short durations, then goes back into this idle state. So in the idle state where minimal circuitry is active, having a nanoPower boost converter such as the MAX 17222 with only 300 nanoamps of quiescent current, the saving is quite substantial. So, for example, an IoT sensing system that powers up for, let's say, 15 milliseconds every minute to take a measurement, this would use an average of 2.5 microamps an hour. So with a CR1216 that has 34 milliamp hour rating, the battery should supply the circuit for about 18 and a half months, or just over a year and a half. Now, adding in the losses of a regulator for, let's say, a non-nanoPower boost converter, even one that has ultra-low current like 1 microamp, you can see that there is a very substantial loss due to the non-nanoPower boost converter of about 40%. Losses contributed by a nanoPower boost would only be around 12%. So these regulators with quiescent current contributes to the power loss and should be as low as possible, so that it's not competing or adding as much to it, but it's more or less competing with the battery self-discharge. And this helps to minimize efficiency losses. So the MAX 17222 is a nanoPower boost converter with True Shutdown. This is our latest low-power regulated power supply designed specifically for IoT and wearable markets. This device operates with a low 300 nanoamp quiescent supply current. It has a 2 megahertz switching frequencies, which allows for small size inductors. There's no external resistive feedback network, eliminating current losses to the output. With its low quiescent current and unique switching scheme, efficiencies even under low loads is above 80%, and this device reaches about a 93 to 95% peak efficiency. True Shutdown completely disconnects the input from the output, so battery self-discharge is the only draw on the battery while this part is disabled. So the MAX 17222 boost converters features a True Shutdown feature, and the device is disabled. Current usage is only 0.5 nanoamps while disabled, making it ideal for storage devices, patches, and things that might have a shelf life of a year or even more. This figure illustrates the basic elements of the 17222 with respect to shutdown and quiescent current. The True Shutdown disconnects the output from the input with no forward or reverse current, resulting in a very low leakage current. With a total of only 0.5 nanoamps leakage current into the device. The effects of the boost converter is reduced in order of magnitude below the battery self-discharge rate. This is complete isolation from the battery to the load circuit. This complete disconnect from the power source to the load means that no other isolation is needed, and the only drain on the battery is its own self-discharge. So how effective is that? Let's do some more calculations. With the use case of a small silver oxide battery rated at 16 milliamp hours and a 10% a year self-discharge using a nanoPower boost converter. So let's say we're designing some device and we want a shelf life of 3 years as a goal, which is 26,280 hours. We're using the MAX 17222 as shown in the figure with a pull-up resistor to enable of 33 mega ohms. The switch shown in the diagram is a 10% battery self-discharge for 3 years results in a 4.8 milliamp hour reduction over 3 years. Subtracting that from the original 16 milliamp hours, this self-discharge will have 11.2 milliamp hours of charge left on it. In addition, let's say the current loss through the 33 mega ohm resistor to ground with the push button shorted is 93 nanoamps. So 93 nanoamps over this 3-year period adds another 1.2 milliamp hours of use of the battery. Therefore, after 3 years on the shelf, the battery still has 9.34 milliamp hours of charge left. So in shutdown, the self-discharge rate of the battery plus the current through the pull-up are the total system loss. So let's see what happens when we turn the device on. So let's say we're operating our application, whatever our circuit is, and as an example, let's say for every 3,997 milliseconds, the circuit averages 10 microamps of current draw, and for 3 milliseconds, it averages a 5 milliamp draw. This would be, let's say, a sensor powering up to take a reading and then shutting back down. Then the continuous average load would be 13.75 microamps continuous average load current, not including boost converter. Total continuous average battery current, adding in for the boost converter, would be 13.75 microamps plus a 300 nanoamp divided by the efficiency of the device times 1 minus the duty cycle. Now, in the use case where, let's say we're using a 2.4 volt battery as an input, and we have the device set at 3.3 volts, and the conversion efficiency is 90%, the continuous average battery current would be a total of 57 microamps. So, even after a 3-year period on the shelf, with a 9.34 milliamp hour left on the battery, using a 57 microamp load current, this battery still has 163 hours or seven continuous days worth of operation left in it. Another thing I want to mention is how to extend usable battery. So in addition to saving power, how can we increase the usable power out of a small coin cell battery? We can stretch more usable energy from a battery by continuing to operate the system at an ultra-low battery level, even when the battery voltage drops below a half a volt. The MAX 17222 will continue to regulate with input voltages down to 400 millivolts, allowing it to pull energy from the battery at much lower levels than ever before, extending the usable battery life. Since the MAX 17222 can operate and boost up to a regulated level with the battery voltage as low as 400 millivolts, there's a problem that arises. Now, the boost converter has an enable pin that needs to be pulled high to enable it. So what happens when the battery voltage drops below the enable threshold of 500 millivolts? How do we keep the boost converter enabled? This device has an internal enable circuit that monitors both input and output voltage and is internally pulled up to the higher of the two voltages. This way, after startup and the system is running, even as the battery is being used and starts to drop to, let's say, 1 or even 0.7 volts, the boost will continue to operate, because once the boost is operating, the enable pin is internally pulled up to the output voltage. This way, the input voltage from the battery can drop to as low as 400 millivolts, which is the boost minimum operating voltage. So for more flexibility, vendors typically provide a resistive feedback string to allow designers to customize the output voltage. This is so the same part can be used in multiple for multiple purposes without having to stock a bunch of different part numbers. Now, this network requires 2 resistors to provide a feedback voltage to the chip to set the output voltage. And this type of network always drains current from the output, no matter whether it's in shutdown, active, or standby modes. This is problematic for ultra-low power applications where every nanoamp saved is important. Let's say we want to set the output voltage of a device with a feedback network of 5 volts at the output using even a mega ohm resistive network, such as a 10 and a 30 ohm. There would still be 125 nanoamps of leakage to ground. So the MAX 17222 boost converter has a unique single resistor output selection method, meaning you can adjust the output voltage via a single resistor, as shown in this diagram. The part uses a 200 microamp injects a 200 microamp current onto the our select pin to read the value of that resistor. It does this for about 600 microseconds, and then it stops. After reading the value, it determines what it is and sets the output voltage. After shutting off, after 600 microseconds, the select pin does not drain any current after that point. This single resistor output setting method is unique to Maxim. One thing we haven't discussed is efficiency. Efficiency is a key contributor to operating power loss. It's very difficult to build a boost converter that has high efficiency during light loads because the quiescent current alone contributes to the low end efficiency. Our nanoPower boost converters are able to service even very light loads down into the 3-4 microamp range and still maintain a 80% efficiency with a peak efficiency of 95%. So the MAX 17222 utilizes a fixed on-time current limited pulse frequency modulation control scheme that allows ultra-low quiescent current and high efficiency over this broad range. So here's a diagram of the output in all three in three power modes. So the MAX 17222 automatically switches between several modes of operation, which are dependent on the load it needs to service. There is an ultra-low power mode, a low power mode, and a high power mode, depending on the load current needed. So here C is a figure of all these operational modes. The output voltage by design is biased at 2.5% higher than the regulated voltage in ultra-low power mode, so that once it transitions to a low power mode or high power mode, the transient doesn't have an effect on the output. You don't see a drop. The low power mode and high power mode are useful for sensitive sensor measurements. That's when these modes will be used, depending on what it's reading. But these would come on in times where you're powering up to read a sensor voltage or you're making some kind of a wireless communication. So the MAX 17222 can calculate and set the value of the load current, or the user can calculate and set the value of the load current and where the transitions occur. So this unique PFM control schemes allows the device to achieve this ultra-high efficiency at all different load levels throughout the range. One thing I do want to mention, this doesn't have to do with I would say power conservation, but it is a feature that I wanted to mention quickly. This is reducing field failures. Many systems are running off secondary cell batteries, and before a battery is plugged in, the input and the output voltages on the circuit are both at 0. So when you plug a battery in voltage jumps immediately to the battery voltage, and the other side of the inductor, the downstream side, as you will ring with a voltage that can be even as high as 2 times the input voltage. This could cause damage to a device. So insertion of a new battery can damage the device or other circuitry. This ringing is caused when anytime you put a step function LC filter. In this case, the step function is created by the insertion of the battery. You'll get this ringing as the energy bounces back and forth between the inductor and the capacitor. So the resonant frequency is determined by the inductor and capacitor sides, meaning therefore with bigger values, you'll get a lower frequency, but smaller inductor and capacitor size, you'll get a higher frequency. So this is something that you need to be cognizant of when designing with these types of systems. So in this boost converter, when the battery is when a new battery is connected, the body diode, a body diode internally disconnect switch prevents the output from ringing. As the boiler turns on, a body switch is first allowed to soft start, ramping the out voltage to its VN minus some small diode drop. After the switch soft starts is complete, the boost regulator continues to soft start, ramping the output up to its regulated output. This output allows enough time for the ringing to subside. One thing I wanted to talk about was multi-source systems. These multi-source systems are becoming really popular with IoT type devices. Some ultra-low power applications such as remote sensors may rely on multi-power sources. However, every boost converters on the market are optimized. Not all the boost converters are optimized for these types of applications. So looking at this circuit, let's look at, imagine an IoT sensor that is powered from a primary cell battery, an RF energy harvester, USB field diagnostic, and even a solar panel. So in this condition, you would need separate converters for each power source, and these high impedance and low voltage power sources typically need to be isolated. In the case of reverse current leakage from the output to the input or output to ground is highly undesirable. So zero output leakage current is the goal in multiple source applications, and there are several reasons why a typical boost converter cannot be used here. One main concern are unwanted current drains on the load line from disabled or unused power sources. So these drains can be from reverse leakage into the part, into a disabled boost converter, or some type of feedback network to ground, or load discharge circuitry. So most commonly used for higher power systems is to isolate each supply would be a simple diode at each boost output. But these diodes are really large, have really large voltage drops, sometimes are usually in the hundreds of millivolts, 500 to 600 millivolts. And this reduces the usable battery voltage, negating any extension of battery life, what we would be hoping to get out of the battery. Ideal diodes are kind of popular and are another way to isolate each boost converter, but they still draw somewhere or have somewhere between 40 and 100 millivolt drop and consume power. Another thing is they need to be controlled through some kind of a microprocessor. So they're not ideal for these ultra low power applications. So I wanted to show this is what would happen if you had a resistive network that I talked about earlier. Noting these are not well used in this type of application. With a network like this, you would definitely have to isolate with some type of diode or ideal diode, or you would have massive losses times 3 through this resistive network to ground. One thing you should watch out for is some boost converters have what they call active load discharge. This can be problematic for multi-source systems. So devices with this feature actively discharge the load while disabled. They do so by enabling an internal MOSFET connecting the output of the boost or the load to ground. So the MOSFET stays in this condition, shorting out the output until the boost is brought out of a shutdown and re-enabled. So this condition would cause a direct short to ground within the system. So be cognizant of these types of features on your boost converters. So the MAX 17222 nanoPower boost converter with its True Shutdown is ideal for these low power multi-source applications. The scheme makes this device the most efficient device on the market while running. The single resistor output voltage select is associated with feedback networks. Complete disconnect from the input to output while in True Shutdown eliminates any need for external isolation components such as diodes, while in this condition in shutdown only uses 0.5 nanoamps of current, which doesn't contribute to any of the battery's discharge rate. So that concludes the introduction to the MAX. This is a list of other nanoPower products that offered. Currently, we offer micro supervisories. We offer op amps, current sense amps, and now these latest boost converters. So in conclusion, our products are getting smaller and smaller, battery size is also getting smaller and smaller. And battery size determines the product size in some cases. New nanoPower boost converters solve the need for these low power, these low IQ requirements. A good boost converter will reduce unwanted current losses, and the MAX 17222 is ideal for ultra-low power multi-source applications. So we have an EV kit for the MAX 17222. You can get that by going to digi-key's website. This kit has two separate circuits on it so that you can test this device with different types of batteries. You can also go to the Maxim's product landing page and learn more about this nanoPower boost and other nanoPower products that we have available. So I'm going to turn this over to Murray for questions.
Okay. Thank you, Robert. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we are answering your questions, please complete the feedback form, which is located on the bottom of your screen. Our first question: how do you control the turn on and turn off of the part without drawing any current?
Yeah, that's a good question. This is Joe Van. A lot of times it gets tricky because, you're powering up a circuit that needs your regulator as the supply. Something has to turn it on. There are some tricks to that. One way to do it is to take a pair of latched weak CMOS inverters and use them sort of as, I don't know if people are familiar with what's called a bus holder, but basically it's a circuit that inverters loop back on themselves, essentially hold their state, whether high or low. And then what you can do to turn on and turn off is just momentarily short the output of the bus holder to ground, or short it to the output or the input. And what will happen is that circuit will draw no quiescent current while it's either on or off, and hold its state, which is a nice feature because, as Robert was saying, you really don't want to have to burn any quiescent current of your precious quiescent current on an enable circuit. So that's sort of one of the tricks. One of the things that's available in the MAX 17222 is an internal pull-up device that was designed to pull up to either the input or the output of the regulator, whichever one is higher. And that's kind of a handy circuit too. Once the circuit is enabled, it will actually sustain and keep itself on. So that's another trick, but something to keep in mind because you're out there trying to save that precious battery life on that button cell powered device, and you don't want to give up any quiescent current just to a switch with a resistor to ground or something, because that'll end up costing you a bunch of current.
Hey, our next question is, what is the recovery timing when the load is switching from around quiescent to 10 milliamps?
Yeah, that's a good question. What we do on these nanoPower circuits is we have a very low quiescent current output monitoring comparator, and the response time of that, we've managed to actually make it pretty quick. It's about a microsecond with maybe a couple of tens of millivolts of overdrive. So not bad. So that microsecond is actually a pretty healthy speed when you think about it, because the output capacitor on this boost regulator is 10 microfarads. So in a microsecond, if you pull a milliamp out of the output the output's not going to, let me think about this. If you pull 10 milliamps out of the output, it's only going to droop by about a millivolt a microsecond. So it's part of it is that whenever you design one of these systems, the output capacitor is your friend. You can always improve transient response by putting a larger output cap on, but again, that's beyond a 10 microfarad cap, it starts becoming a size issue because you really want to use the smallest output cap possible. But yeah, typically the response time is about a second or about a microsecond with a reasonable 20 millivolt overdrive. And what will happen is it'll go from a mode where it's just monitoring the output for small movements to a mode where it's ready to go ahead and ramp that inductor current up to an amp. So yeah, that's what's going to happen.
Hey, listener David asks, what is the outcome to the MAX 17222s of multiple sources being on simultaneously?
I think the application circuit is when you have, say, multiple MAX 17222s all driving a load, and what will happen is if you have valid sources on, say, 3 inputs, like Robert was showing, maybe you have a solar cell and a coin cell battery, and maybe there's also I don't know what else might be there, a RF scavenging circuit of some kind. What will happen is if all the sources are valid, then whichever output has the slightly higher regulation threshold will go ahead and force the output to that regulation threshold, and the others will just sit idle. The circuit has a 2% overregulation threshold during this ultra-low power mode that we spoke about. The reason is because you'd like to give yourself a little bit of margin on a load transient that was like previous mentioned. If you suddenly throw on a 10 milliamp load, you want to give yourself a little bit of margin to swallow the load transient on the output. But in general, all the outputs are just going to hover around 2% high. So whichever one happens to have a slightly higher threshold would draw the current. But if you don't really have much load current, probably doesn't really matter which source you're drawing from. If you're lucky, hopefully you're doing it from one of the renewable sources and not the main battery, because you always want to save the battery current whenever possible.
Listener James asks, Will these boost converters contribute much noise to the system?
Oh yeah, that's always a tricky one because typically when you're doing very low power circuitry, what's happening is the switching is occurring for impulse, and then the circuit might go to sleep for over a second. So is that when you have a switching regulator on and it happens to find a home switching in the frequency near the audio range, sometimes you can hear an audible noise on certain capacitors that have a sort of a piezo effect where they're changing their physical dimensions at some small dimension. They're making essentially a noise that's going along with the switching frequency. So a good choice of components. Some components are worse than others. In terms of electrical noise, of course, the regulator is designed to pulse and then go to sleep. So and there are multiple options nowadays for nanoPower boost regulators. So what you want to look for is one that actually or maybe just 1 or 2 pulses. You don't want to burst at a megahertz and overregulate, say by several hundred millivolts and then shut off. But again, it's always a trade-off on the design, so you really want to look for your best option there. Some people use linear regulators on the output, but then of course that takes away the advantage of the nanoPower because you're burning idling current in the linear regulator. So there's kind of a trade-off there. But the noise is you want to look for a part that delivers the smallest packet of energy between and then goes to sleep, because each packet of energy is going to have to be stored on the output cap. And so if you want to keep the output noise to a minimum, what you want to do is choose that boost regulator that has the ability to deliver the smallest amount of energy and then go back to sleep.
Our listener says, you stated the efficiency was 90% with output voltage to input voltage at 3.3 and 2.4. What is the efficiency of input voltage at 0.4 volts as specified?
Yeah, the 0.4 volts is actually about where your break even is. It gets difficult to deliver. That's kind of where it runs out of gas. So efficiency tends to drop as the input voltage drops. For a certain amount of on time, and the inductor current tends to be up in the hundreds of milliamps. So the problem gets to be that when you pull that slug of current out and you're using very small components, sometimes the ESR of the inductor alone is a couple hundred milliohms or more. I've seen an ohm. So, the efficiency is really limited by your stomach for how much, how great of an inductor you can find, and what's that series resistance of that component? What's the series resistance of the battery? Things like that. So the efficiency is almost, it's probably in the tens of percent by the time you get to a 0.5 or 0.4 volt input. What we're really looking for there is you're just trying to get that, squeeze that last bit of energy out of the battery. So that was the thinking there. When you're running above, say, 1.5 volts, efficiency can get back up into the 90% range. But in general, the efficiency drops with input voltage because the parasitic voltage drop through the inductor resistance, through the battery source resistance, becomes significant compared to the battery input voltage. So if you have a 1.2 volt, if you have a 1.2 volt input battery voltage and you happen to have 120 millivolts of parasitic resistance drop, you're going to lose 10% efficiency there. It's basic physics, and it's kind of difficult to get rid of that. So
Listener James asks, what is the minimum startup voltage input required?
Yeah, so the startup voltage, there's a MOS devices typically need a little bit more enhancement than a bipolar. So what we did was in our design, we provided a low voltage bipolar startup circuit, and that circuit starts up around 0.9 volts. And the source, what will happen is the boost regulator with that oscillator is capable of drawing current out of a source that has a very high impedance, and it basically does it by pulling all the current out of just an input decoupling capacitor. So what will happen is it'll suck the energy out of the input capacitor and provide it to the output capacitor until the input cap voltage drops down to around 0.85 volts. Once it gets to 0.85 volts, the circuit will stop trying to boost, and it will let the input capacitor recover back up to 0.9 volts, and the cycle will continue. So we have thought about that. We realize that in these nanoPower applications, when you have a coin cell that has a very resistive source, you really want to have a circuit that can extract the power when the input source is down at around 0.9 volts without basically just going into some kind of a latch-up state and drawing the rest of the current out of the battery. So what will happen is, in summary, the input voltage will sort of ping-pong between 0.85 and 0.9 volts as the circuit tries to turn off of the input cap, and then the source will just, it will hopefully be recharging the input capacitor at a rate fast enough to support whatever load you want. But that's kind of the limits to how low the input voltage can be during regulation.
Listener wants to know, is there a load battery indicator with the 17222 that can be used to trigger a load circuit?
There is not a low input voltage detector. Basically, the output tries to regulate with whatever it has, and we don't have a reset circuit on the output of this regulator. Sometimes you'll see that parts will offer a power OK reset output, typically something like an open drain output. That can be useful. One thing to watch out for when you have a power OK output, an open drain output, is that what typically happens is when your circuit is reaching end of life and the circuit is kicking on and off, what will happen is it'll actually discharge your battery, telling you that your battery is low, because the pull-up device will actually burn current. So, but no, the 17222 doesn't have that feature, but there may be parts that have a feature like that.
Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank digi-key and Maxim for sponsoring today's event, and of course all of you for joining. Have a great rest of the day.